So folks, we will be giving you a demonstration of VisualCAMc in Onshape in just a moment. And if you have any questions during our demonstration, you're welcome to post those questions in your questions panel, and we'll try to get those questions answered to you as quickly as we can. So without any further delay, I'm going to go ahead and jump into a demonstration here. So what you're looking at is an assembly of multiple different parts that has been modeled and built in Onshape. You can see that we are looking at the assembly on this tab here. So I'm going to switch over to the tab that says housing in here, and this is one of the components we will be looking to machine here or generate toolpaths for machining for this particular component. So I'll walk you through the steps on how we go about taking this CAD data, the part that you model, and how we can turn this into a machining data, which you can then send it out to your CNC machine with the help of VisualCAMc. The first step is you would need to subscribe to VisualCAMc app by going into App Store from Onshape, and I'll show you how to do that towards the end of the demonstration. So once you have subscribed to the app, you just go over from your document, you insert a new element, you select Add Application, and then choose VisualCAMc. So VisualCAMc will automatically load in as a new tab within the same Onshape document that you're working in, and it will give you the ability and controls to load a part or a part studio from your current document that you're working with. So in this particular example, I'm going to pick the housing as the part I would like to program and generate toolpaths and post-process this out to a CNC machine tool. So as you can see, the model is loaded. And by the way, as you notice, everything is happening on the cloud. Nothing is being driven locally here. It's just from a web browser. And once the model is loaded in here, the first step you want to make sure is you can see all of the interface of the CAM being loaded. You have your machining browser interface, which appears over here in the left pane. Very similar to what you folks, if you've used our desktop product, you're seeing a machining job, and you'll see all of the entries in here. You also have a Tools tab where you can define different types of cutting tools. You can also bring in a library of tools. So the workflow typically is working your way from left to right as you work through these toolbars across the top. The first step is to establish your coordinate system for machining. So as you load the model, VisualCAMc automatically inherits the orientation of the coordinate system, the way which the model was built. So you can see that the blue arrow represents your z-axis, the red arrow represents the x, and the green represents the y coordinate axis. Now in order to be able to program this part, I would need to orient my coordinate system so that the z-axis is normal to this face where the holes are located. So I'm going to use the controls in the machine coordinate system tab in here. I'll be rotating it, and as you can see, it's updating the coordinate system orientation, and I'm going to save this in here. Now once the coordinate system has been established, in the next step, we would like to select our post processor. VisualCAMc includes post for over 300 plus different machines and controls, which covers a wide range of machines that are out there. You can also custom edit posts and build new posts and add them to it here. You can also have your favorite 5 post list of machines can be set right in here. And for this demonstration, I'm going to use Fanuc as my controller. If you'd like to use one of your custom built posts, you can use load from files option to import the post processor into VisualCAMc. I'm now going to select close, and you'll notice that the post processor information is updated in the machining job. In the next step, we would like to build our stock material. So we're going to select stock, and you can define a stock either as a box or a cylinder. For the part that we are programming today, we would be using a box stock in here. And as you look at the stock, extents is automatically determined based on the part that's being programmed. I'm going to add a Z offset to the stock, and this is automatically being displayed in real time on your graphics screen as you notice it. I'm going to hit save. In the next step, you would like to establish your work 0 or program 0. This is the origin that you would establish when you do a tool touch off or your work coordinate offset for machining the part. So we call it work 0. And I'm going to set this to the stock material, We'll pick the highest Z for the face, and then the corner, I'm going to pick the southwest corner. So you'll notice that the coordinate system origin is now set to the top face and the southwest corner. And if you'd like to output your work offset as a G54 or a 55, you can specify this in here and then save. So each of these steps that you did is automatically recorded and saved in the browser window here, and you can always go back and make changes or edits to it. Now we'll take a look at the different operation types. VisualCAMc offers a wide range of methods in 2.5-axis programming, starting with facing, pocketing, profiling, V-carve roughing and finishing, engraving, slot machining, chamfering, fillet machining, hole pocketing, hole profiling, thread milling, and T-slot machining. Now in 3-axis, we have different types of 3D machining methods, starting with roughing. We call it Z-level roughing, also known as horizontal roughing in our desktop products, Z-level finishing, parallel finishing, radial machining, and spiral machining. And we do offer hole machining, where you can do drill, deep drill, countersunk, brake chip, drill cycles, tap, bore, and reverse bore operations as well. Now to program this part, the first thing I'm going to do is a facing operation to face the material out in here. So we'll go into 2-axis and we'll pick facing. Now this automatically displays the controls for facing, where you can start by selecting a tool. As you can see, it's a tab-driven interface. It's very easy to use. You can define your tools by going to the Tools tab, where you can create tools of different types. We support ball and mills, flat and mills, corner radius tools. V-mills could be used for engraving, chamfer machining, thread mills, taper tools, face mill cutters, dovetails, fillet mill tools, lollipop cutters, and of course you have the drill, center drill, reamer, tab bore, and reverse bore. So you have a wide range of tool types that you can create, and you can either create your tools by defining your tool properties in here. We can specify the tool diameter, the flute length, the shoulder length. You can input all of these parameters in here by just typing them in, or you can even save the tools into a library and load them from your library. You can also assign your tool properties, like your tool number, your height offset register, your coolant type. Each of these can be set for each tool, and as you save this information, it stays in the session. I also have a library of tools created. I can import my libraries by just importing a CSV file, and I can select the tools that are in my library and drag and drop it into the tools and document. So that's how easy it is to load a library of tools and add it to your document. Now let's switch back to our machining job, and you'll notice that for the facing operation, it automatically restricts the tool types based on the operation type. So for this particular operation, I'm going to use the face mill tool, and as you select the tool, you'll see that the tooltip automatically displays your tool number, your holder information, tool diameter length. All of the information is available at your fingertips. The next step is to jump into the Feeds and Speeds tab, where you can specify your spindle RPM, spindle direction, your feed rates for plunge, approach, engage, cut, retract, and departure. Coolant type can be set right here as well. And then you go down to a clearance tab, where you can establish your clearance definition. And when you select this tab, you'll automatically see the clearance plane is made visible in the graphics window. You can adjust these using any of these controls. And then finally, we go down to parameters, where you have 4 sub-tabs where you can specify your tolerances, your cutting conditions in here, your cut patterns, your step overs. Each of these parameters can be set. You have the finest amount of control and granularity that's available in here. You can control your step overs, your entry and exit. You can specify each of these parameters in here. So you have all of the details and the controls that you're looking for, which is available equivalent in our desktop product. So I'm going to pick Generate, and the toolpath is being computed, generated, and it's delivered back in here. So you see the facing toolpath appearing in the graphics window. We can also toggle the display of the toolpath by using the controls over here on the side. Now once the toolpaths have been generated, you would like to go ahead and run a simulation. So selecting the operation, right-click, and simulate performs a cut material simulation. You can control the simulation speed. You can also have controls for pausing and simulating to end. So once the simulation has been completed, we'll exit the simulation and we'll program a few other operations. So we see a few cavities on the model in here and also some core regions. So to program these cavities, since they're sculpted areas and there's fillets on the model, so I'm going to start with a 3-axis roughing operation. So we'll pick 3-axis and Z-level roughing. And in this dialog, I'm going to pick a tool, so we'll switch over to a 1/2 inch flathead mill. Again, the workflow for defining feeds and speeds and clearance is very similar to what you noticed in the previous operation. We'll go into parameters where you can specify your cutting conditions. You can choose to automatically have VisualCAMc determine facing cut patterns for core regions and cavity cut patterns for cavity areas in a model. And each of these can be set right in here. So we have different cut patterns for cavity regions, starting with offset, offset spiral, linear, and even high-speed cut patterns available in here. You can control your step over parameters for each of these cut patterns. You could control your cut levels where you can specify how fine you want it to step down. You can specify additional containment parameters in here, and each of these can be set. And of course, you can control your entry and exit and any advanced cut parameters, and then select generate to generate the toolpath. Now the toolpath is being computed and delivered back, and you can see how quickly and efficiently you're able to generate the toolpath. So there's scalability available since you're running in the cloud. You can, depending on the intensity and computation involved, it can automatically scale up and scale down of the use of the servers. So the toolpath has been generated in here, so we'll go ahead and run a verification. So we select the operation, right-click and simulate. We'll run a cut material simulation. You can toggle the display of the toolpath visibility on or off. You can also change the simulation speed in here as you're simulating. And of course, you can rotate the view during simulation. And this is all happening in real time. You can do a pause, then hit simulate to end to run through the simulation. So stock has been roughed out. So the next step is we can go ahead and program a few additional operations in here. So I would like to finish off the front areas in here. So I'm going to use a profile operation. Select 2-axis and profiling. And again, I'll use the same 1/2 inch end mill for it. Set the feeds and speeds and clearance. Then go down to parameters. Now for the profiling operation, I would like to restrict the toolpath to a specific area. So I'm just going to right-click on this, and it'll automatically select a chain of edges that are planar to the face. I can specify my cutting directions, cut start side. For the depth, I can actually pick it from the model. Graphical selection by just making 2-point pick. And the total depth is determined. We'll break it up into multiple steps, specify entry and exit, and then generate. So the toolpath is generated, and you can display the toolpath by toggling the visibility on. Right-click and simulate runs the cut material simulation. Now to program these holes, I'll go into a drilling operation, so hole machining and drill. And depending on the operation type, you'll notice that the tool types available for drilling are drill, center drill, or a reamer. So I'm going to pick a 1/2 inch drill bit. Again, specify my feeds and speeds and clearance, and I'll jump into the cut parameters where I can just select the holes in here for drilling and specify the depth and additional parameters and then generate it. So the drilling operation has been generated. I'm going to hit simulate to run simulation. Now finally, to finish the features on the cavity in here, I'm going to use a 3-axis operation, and we'll start with axis parallel finishing. And for finishing operations, typically you would want to use like a radius tool, like a ball and mill or a corner radius tool. So I'll pick a ball mill 1/4 inch, set feeds and speeds and clearance, and then we'll go into the cutting parameters. I would now like to contain this finishing operation just to an area, so I'm going to just select a bunch of edges in here for containment. Specify your cutting parameters like your angle of cuts, step over distances, and finally generate to generate the toolpath. So the parallel finishing toolpath is now generated. Now to finish these fillets along the sidewalls, I'm going to use another 3-axis finishing operation in here, and this would be a Z-level finishing operation. So you could program a combination of 2 and 3 axis operations. I'm selecting the same ball and mill we used for the parallel finishing. And for now, for this, I'm going to pick this region in here to contain the tool paths. The regions have been selected. I could specify the cutting conditions in here. I'll use a step over of 15% and generate it. I'm going to skip the programming of these holes because the process will be very similar to what we did in the drilling operations. I'll run a simulation of the parallel finishing operation in here. Right-click and simulate. You could always adjust your simulation speed to have it go faster or slower. Or if you want to pause the simulation and skip it to the end, you can select pause and then go to end. So you have all of these controls in simulation. And exiting the simulation will save the cut model and display it on top of the part while in the programming window. Now once you have all these toolpaths and operations programmed, the final step is we need to communicate this to your machine tool. So we do that by a process called post-processing. And like we've already selected a post-processor at the start of your programming workflow in here, we can post it out to the machine tool. So you can either select the entire setup to post-process all of the operations in the sequence in which you programmed, or you can post individual operations as well. So I'm going to highlight the setup, right-click on it, and then select post-process. So the toolpaths that you programmed are being post-processed, and the generated file is downloaded to your local computer, and you can now view this in a text editor of your choice, and the program is now ready to be sent over to your machine tool in here. Now, I also want to point out the VisualCAMc product offers the ability to do 3+2 programming, in which you can program the part from multiple sides or multiple different orientations. So in the first setup, we program the part looking down from the top here. If you have features that requires machining from additional sides, like you may have features that needs to be machined from the bottom side or from additional sides in here, you can create additional setups by adding a new setup. So this is called 3+2, where you're locking the orientation for machining to different planes or different orientations in here. In this case, I'm going to rotate it by 180 degrees about the x-axis in here. And you'll now notice that the z-axis is now pointing normal to the bottom face of the part. I'm going to go back and insert a new work 0 in here. I'll pick a higher Z in the southwest corner, and now I can add operations to program features in here. So I can start out with a roughing process for the bottom face as well. To program these pockets, I can select the tool, establish feeds and speeds, and I can pick areas to restrict or contain toolpath by just selecting boundaries and generate the toolpath in here. So you could program your machining operations from multiple by creating setups, and you can simulate them from each of these orientations as well. So the 3+2 ability allows you to program from multiple different orientations. If you'd like to program these features from different orientations, you can still do that by creating multiple setups and programming them.
Uday, so this means that the machine itself will automatically flip the part over, depending, obviously it depends on the machine, but when it goes from setup 1 to setup 2, is this something that the machine just goes automatically to the next step?
That's a great question, Joe. So if you define the machine tool as a 4-axis, and if you're using a 4-axis machine where the part can be rotated on a rotary table, yes, it will output the the rotation angles to rotate the table or the rotary axis by 180 degrees in this particular case. If you define the machine tool as a 5-axis machine tool, then it will each of the setups will output the orientation to get to that. If you only have a 3-axis machine tool, the user would have to refixture the part to manually orient it, and then you can basically post-process each setup out as a separate file.
Uday, can you show the simulation in the second setup, please?
Absolutely. So I'm first going to go ahead and simulate the Z-level finishing, which I haven't completed yet. So once I'm through with the Z-level finishing, I will be able to go ahead and simulate the finishing of the setup 2 as well. So I'll just do a pause and then simulate to end. So that completes the simulation of all the operations in the first setup. And now we'll go ahead and run a simulation of the setup 2 as well.
Once you start building these simulation models, obviously the polygon count on all of these models are going to start increasing, and you're going to see a little bit of a performance hit. That's exactly what you're seeing right now, because we are actually saving the cut model on the server and you know, moving this back and forth from your desktop or to your local device to the server.
So once we have the simulation, the cut model generated for the first setup, we would then switch over to the next setup in here to be able to simulate the next setup in here as well. So which I'll be able to demonstrate in just a moment. Now, while we are waiting on that, I do want to quickly show you, you know, some of the you know, type of toolpaths that you can generate on different class of parts or complexity of models in here. So for example, here you're looking at a high-speed cut pattern toolpath that can be you know, employed in a roughing operation in here, where you can generate toolpaths for very efficient toolpaths for roughing, where it's generated by use of a constant tangential arc, so which you can run it at a higher feed rates, and it basically prolongs your tool life and reduces wear. So here is the simulation for the high-speed cut pattern. While you know, you're looking at the simulation, here you can see that it creates constant tangential arcs in the simulation, as well as the cutting motion. So this is available in both roughing and pocketing operations, the high-speed cut patterns. So you can see with VisualCAMc, you can program a wide range of parts, wide class of parts, ranging from simple to complex geometries.
And just in case everyone didn't really catch what Uday did, this is the whole point of the cloud again, is that, you know, this is all happening simultaneously. So you know, machining is very computative intensive task. Sometimes toolpaths can take, you know, every system will take a long time to calculate, but he can run it multiple sessions here in different tabs. You can go to Onshape and continue to work. You know, you're not stuck with having everything run on whatever computer you're using, and you just have to sit there and wait for it to finish. So.
Okay, thank you, Joe. Folks, as promised here, I have the cut model ready for the setup number 2. So I've switched back to the previous screen. I'm going to select the setup 2, the operation Z-level roughing, and I'm going to just rotate the model view in the graphics screen before I run a simulation. So I'm going to select simulate. So you can see now the simulation will show the cut material verification for the setup 2 as well. So once you've simulated the first setup, you can select the operations under the second setup and start your simulation. Again, folks, if you do have any questions during this demonstration, please feel free to post those questions in your questions panel, and we'll do our best to get them answered for you. So you can see that the bottom side is now being simulated, and you still have the result of the simulation from the top half.
The product is fully associative, and so right now I just created a version. So everything that Uday did on that part on the worm gear, you know, it's just a little hard in GoToMeeting for us to. I mean, I would just, yeah. So it's you know, in GoToMeeting, switching back and forth, I'm just going to skip it. But you can see that I'm up there in the tab showing that I'm a user in this design as well, and I can make changes to the part. I actually saved the version. We're in a different branch. So, you know, everything about VisualCAM is honoring all the power of Onshape. So we're, you know, each branch can have its own machining. Each version is saved at that stage. So it's a nice, simple, and proper solution. So in this case, long story short, you know, we have potentially, we want to add a little clearance. We have a clearance problem in the assembly. So I'm going to make a couple changes to this very quickly, and you'll see them visually show up. Let's do this. Make this 0.2. Okay, so I just wanted to do something that is very visual, and you can see that the part now has a much stranger angle. And let's just say, for the sake of argument, this was a clearance problem we had when this part goes together. So very common iterations, right? So I'm the design engineer. I made a change to the part. Now the question is, what happens to all those toolpaths that we created before?
Okay, so folks, since there were some design changes made into the model, I'm going to switch over to the VisualCAMc tab, and you'll notice that it automatically identifies the change in the geometry, and also the user is notified about this change in here. So once you have the changes notified, you just have to go back and regenerate your machining operations, and the toolpaths are automatically being updated on it. So you just have to right-click and regenerate on your setup to regenerate each of the operations in here. And they're automatically updated. So that's how simple it is. So if you make a change, you go back and regenerate your operations.